Okay, students, welcome back. Okay, now you have worked with database operators, things like that logical indexing, so you can just extract the values from the archive that you want. Now that you have the data limited to just the values that you need, Octave is going to provide you a whole bunch of different tools to help you compute various descriptive statistics. In some ways it's almost too easy because they provide so much of it for you. It's really kind of the technique of just knowing what it is you want. For example, if you already have an array of data, like you have now after doing the logical indexing and knowing what you want, the mean is a relatively straightforward thing to create. Well, thinking back to the previous module, what you're really computing is the average. You're adding up the numbers and dividing by n. That's an average. It's an estimate of the mean, but the function that they use to actually compute the average is called mean. And so, for example, if I had an array, like let's say this my data array was already trimmed to just being the observations that I want to see, you know, the station I want, the year I want, the month I want, whatever, then I could just say that some variable a is equal to the mean of my data set across all the rows, column 5. I just want to take the average. This would be the, you know, if I narrow down to just the period that I meant, their mean would compute the average across column 5 of all of the rows. Alright? Now, what I want to do to show you this is I am going to go over here and I am going to show you that I am going to run Octave, and I already have made a little program called example 3, which I'm not going to show you at this time because example 3 works very much the way I want project 2 to work for you. I don't want you to see it just yet. And I want you to see that when it runs, it has created, well, I started off with some data set. The full 8-year data set had 485,000 lines in it, and I narrowed it down to just 2012, and that had 59,000 lines in it, and I narrowed it down to just one station, that happened to be station 506, which was Howells, and that left us to just 366 observations. And then I did a data quality thing where I limited myself to just observations that weren't missing. I pulled out any missing observations. It took me until first I got rid of ones where the minimum was missing, and then I got rid of ones where the maximum was missing. And in fact, I still ended up with 366 rows because there was no missing data from Howells on that particular year of 2012. So I now have 366 observations of the maximum minimum temperature for each, one for each day of a leap year in Howells, Nebraska. Alright, so now I can start doing things like computing averages and whatever. Like I could compute the average across my array, which I'm using the data final one. That is the one that I've done all that quality control and so on. I'm saying all rows column 5. This column 5 is the, let's see here. This is going to compute the average high temperature under those conditions. I mean, it's 2012 in Howells. And if I run it, it tells me that the average high temperature in Howells is, the answer is 18.038. Okay, or I could have said, average high temperature equals mean of my final data across all the rows in column 5. That might have been an easier way to do it. That way I have a variable with it there. And I could do the same sort of thing with the average low temperature. I could have said like average low temperature in Howells would have been the mean of data final all rows column 6. And in fact I get that the average the average low temperature is 4.1 degrees Celsius at that station. Okay, so we can compute the average high temperature, or we can compute the average low temperature, but what about the average daily temperature? Like, what is the average temperature on a particular day, or the average temperature in July, or the average temperature in 2012, or something like that? That's actually not a variable that's in our data set. We have records of every day's high temperature and every day's low temperature, but we don't actually have in the data set that we're using the mean temperature for each day or whatever. That's something we're going to have to find a way to estimate. We're going to have, for every given day of the year at our station, we're going to have some way, well, for any one of our 400 and some odd thousand observations potentially, we need some way to estimate what was the average temperature or mean temperature each day at that station. Now, ideally, we would have the data to back this up. Ideally, we'd have something like this, where maybe this is 24 hours. I just faked this. This is just the numbers I played with on a spreadsheet. Ideally, we would take like 24 hours of temperature data from a station hourly, and we could add them up and divide by 24. We could just compute the arithmetic mean, the average. Even that would only be an estimate of the mean, but that would be a pretty good estimate of the mean temperature. The true mean temperature would be, well, we'd have to take more observations than that, right? What if we took the temperature observation every 30 minutes? Well, then we'd add them all up and divide by 48. Ooh, it's still not enough. What if we took, that's still an estimate of the mean temperature. What if we took the temperature observation every 1 minute, added them up and divided by however many minutes there are in a day? No, that's still an estimate. There's no way to get what the true mean temperature is, but we would have good ways of adding it up and dividing by, however many observations, and they'd be a better estimate. That was what we would do ideally. But these stations in this particular data archive don't have that kind of information. All they have is the high temperature and the low temperature for every given day, like the 2 points that I sort of highlighted there in purple. That's all we've got, the temperature maximum and the temperature minimum. How are we going to use that little bit of information to come up with at least a decent estimate of what the mean temperature for the day was? Well, one thing we could do is just sort of say that the daily mean temperature was estimated by the average of the maximum and the min. Just add the maximum to the minimum and divide by 2. Wow, that doesn't seem right. You'd be shocked to know that that's in fact how we do it. In meteorology, like when you learn about climate statistics and things like that, in fact, for various reasons, what they keep track of is the maximum and the minimum. They add the 2 up and divide by 2. That might seem really primitive. I'm guessing you're kind of shocked to find out that's how we estimate the mean temperature on any given day. But actually, it can be proven that that is not a bad estimate of the true mean temperature on any given day, as long as the temperature trace over the course of the day, if you actually had a recording thermometer and you could see every hour or every half hour or every minute or whatever, as long as nothing just too weird happened, it can be proven that actually this simple estimate of the mean, maximum temperature plus minimum temperature divided by 2, is actually not terrible. It isn't quite the M view, the minimum variance unbiased estimator, but it's not bad. It's actually not terrible. I mean, for example, if we took this little temperature trace that I just sort of made up over here in Excel, where I had it getting cooler during the night, warmer during the day, and so on, if I actually did my little nifty technique and added them all up, 24 observations, and computed T-bar, the actual average of those 24 observations, I get 16.8 Celsius. And our little estimate of this that we just get by taking the maximum and the minimum is only 17.15. I mean, yes, it's not the same, but that error is not really all that big. I mean, it's like 0.3 degrees Celsius. And, I mean, it's not an error. I mean, T-bar is an estimate, too. We don't know what the true mean is. Being off by that little bit, there's no bias to it. Sometimes it'll be high, sometimes it'll be low. On average, it'll average out. This is not terrible as long as the temperature trace does something realistic. Like, it can actually be proven that this is, in fact, a minimum variance estimator, unbiased estimator, if the temperature trace follows like a sine wave, with a minimum and a maximum and so on, or a simple sawtooth wave. Simple kind of temperature traces that look realistic, it works just fine. I mean, if I had something goofy like this, where the temperature trace was, the temperature was basically steady for 24 hours, except for 1 hour that was way higher. Okay, in this fake 24-hour period, the average, where I added up the 24 observations and divided by 24, is only 12.6 degrees Celsius. But my technique of taking the maximum and the minimum here, where the maximum is 20 degrees Celsius and the minimum is somewhere around 12, only leads to 16 point... Okay, we're off by, what, 3.5 degrees Celsius. That's a pretty big error. On the other hand, that's not at all a realistic temperature trace. And so as long as the temperature trace is real, this little technique of add the maximum to the minimum and divide by 2 is not bad. And in fact, that is in fact how we do that kind of climate statistics. So if you are tasked in your project with finding the average daily mean temperature, what you've got to do first is compute this estimate of the daily mean temperature. So every day in your arrays, you've got to come up with an estimate of the mean temperature by taking the high and the low, add them up and divide by 2. Okay, that's not going to involve loops. Okay, you're going to be adding this column to that column. You're going to make a new array, we'll call it daily mean temperature, where you add column 5 from your data array to column 6 of your data array and divide by 2. Once you've screened it for missing observations anyway. So if you're going to be doing this, just to kind of parse this through here, first compute the daily mean temperature, then take the average of that. Okay, so like if I wanted to compute the daily mean temperature for July at my station, first screen for that station, then screen for the month being equal to 7, then get rid of all the ones where the maximum is missing, then get rid of all the ones where the minimum is missing, and then what's left is a subset, a number of the observations that are for that station and that month, etc. Now, for every day that's left, we're going to add column 5 to column 6 and divide by 2 in some new array. We'll make some new array that is equal to data column 5 plus data column 6 divided by 2. Then take the average of that. Pretty slick. Octave is full of nifty tricks like that. Okay, so the command to create an average is peculiarly mean. On the other hand, there's lots of other things we can do too. We can compute the median. There's a function already built into Octave called median, where if I've got a data set, I'm calling this my data here, where I've narrowed my data down. I've already done my data set database operations on here to limit it to the years or the month or the stations or whatever that I want. Then I have saying that I have this array, which I'm calling my data right now. Here I'm computing the median of the data that are left in column 5. Okay, all rows, each of which is a different day, but we're computing the median of the data in column 5. So where does the value of column 5 such that half of the values are less than this and half are more? For example, the way I have it written right there right now, that would be the median high temperature. So column 5 is high temperatures for each day. If you wanted to know for some reason the median high temperature, this is how you would do it. Or for example, you could switch over to column 6 and call this the median low temperature. Great. Okay? Or you could, which would actually be a more likely problem to actually have to solve it like at a job or something, what is the median daily mean temperature? So if you knew that, so you're going to have to go through this whole process again, where you compute the mean, this estimate anyway, of the mean temperature at each station by, at every time you have left in your array, you're going to have computed, the mean temperature for that day by adding the maximum and the minimum and dividing by 2, and then do the median operator on that result. What about the mode? Sure, you can compute the mode. I bet you're not so terribly surprised that Octave already has a mode function built in. It's called mode. And the whole thing works exactly the way you would expect it to work. If you've already narrowed your data down to a new array, well, I'll call it my array. It has the right year, the right months, or the right stations, or whatever in it. Okay, it's been screened already for missing data because that'll really mess up some of your statistics. Then mode will compute the mode of column 5 across all rows. So like you could get the mode high temperature. What is the most common high temperature? You could get the mode low temperature by doing that kind of operation across column 6 rather. And you could do the same sort of thing to find like the mode daily temperature, a mode daily mean temperature, where you've already computed the daily mean, well, at least your estimate of the daily mean temperature, and then computed the mode across that new variable. All this would work, okay? And now that you've kind of picked up the pattern from all of this, it's actually not so hard to figure out what other descriptive statistics in Octave would look like. For example, if you want to compute the sample variance of the observations that you have, that is var. So the sample variance of the high temperatures for each of the days is var of column 5. Or you could compute the sample standard deviation, which is STD. Or you could find the maximum. What is the highest high temperature? Do the maximum on column 5. Find out what the highest temperature. Or what is the highest low temperature? What is the temperature that it was, that was the warmest night, okay? Or whatever. Or what is the lowest maximum temperature? What was the coldest winter day? Things like that. Maximum is a good function. Min, to find the minimum, use the min function, which is built into Octave. All nifty stuff. Interquartile ranges are built into Octave. Feel free to use IQR, and it'll return your quartile ranges. You might have to see what it gives you. You may have to. I think it probably gives you. No, that interquartile range is just a scalar. It should just give you a single number. X equals the interquartile range. Should work. Skewness. Once we start talking in the next lecture about histograms, you might be very interested in knowing how skewed your data are. Well, there's a built-in skewness function. Feel free to compute the skewness of the high temperature distribution, or the low temperature distribution, or the mean temperature distribution, or whatever. Cool. Okay. Now, you have just been given a huge box of functions that are built into Octave that you're going to be able to use for all kinds of different purposes. And once we have them, I mean, we can use them to compute all kinds of things in Project 2. Let me just ask you a quick question about it. And, for question 3, the Octave function that computes the average of an array called X is A, average X, B, AVG X, C, mean X, or D, mu X. Alright, so pick one of your answers from the questions, the choices below, and get a little feedback before we move on to question 4.